This is part 3 of the day 64 equilibrium rice table assignment, and we're almost done with it. We're getting there. Okay, so here we go. The equilibrium constant for a given reaction is 0.561 at 800 K. If the initial concentration of HI is 0.5 molar, what are the equilibrium concentrations of each of the species? Okay, so here's this reaction. We've seen it before. So let's go ahead and write it up here. Okay, and they're giving us the equilibrium reaction for the HI right here. So what makes this problem different than the previous problems is they're not giving us any concentrations for the reactants here, so those are going to be 0. So this is a reaction that's going to flow from right to left. That's the only direction it can flow. So you might ask, well, why didn't they call this the reactant, put it over here, and call these the products and put it over there? They could have, but then that would have changed the equilibrium constant. The equilibrium constant for this, it applies to this reaction with these two being reactants and this being the product. So that's why it's done that. I'll make a comment about that as we get a little bit into the problem as well. Okay, so we just start filling things out here. We have coefficients of 1 here, just to emphasize that. So that's going to make this, these are increasing. That's what you got to remember on this, and this is decreasing. So this now is going to become plus 1x, because this is increasing. This is also going to be plus 1x. And this is going to be minus 2x. Alright, so just be sure you understand the pluses and minuses and why they are the way they are in this problem. Okay, so we come down here, and I'm going to leave off the 1 now. Okay, so be sure you're comfortable with how we got these. It's just a subtraction there, just a simple addition there. Now we write the law of mass action for this. Okay, so there's the law of mass action. Let's make a comment about the direction of this reaction. We have products on the top, and we have reactants, even though they don't have anything to start with, on the bottom for this equilibrium constant of 0.56. If we had reversed this reaction, because it looks like it's really, we're starting with all this and none of this, so why didn't we turn the reaction around and say 2HI on the left, and on the right we have H2 plus I2? You could have done that, so what would that have done to this equation? It would have flipped it. These would have become the products. They would have been over on the right, and they'd be on the top, and this would have been the reactant. This would have been the reactant. It would be on the bottom. You would have flipped this over. So if you're going to flip this over, what would you have had to do then to the equilibrium constant? You would have had to take the reciprocal. And remember, that's one of the principles we learned about how these reactions work in equilibrium, is that if you reverse the reaction, you take the reciprocal of the equilibrium constant. Okay, so it's just a comment about this. We're not going to do that, but we're just saying, you know, if you're asking why wasn't this considered the reactant, since it's all this and these become considered the product, you could have written it that way, but then you'd have to take the reciprocal 1 over 0.56, which is whatever it is, and that would have been your equilibrium constant for that reaction. Okay, all right, let's go ahead and plug in now. So we have this, we have to square it, and this is xx, so we can just call that x squared. It's x times x, x times x, so let's just call that x squared. That makes solving the problem a little bit easier. All right, and that's going to equal this, the Kc, for the reaction going in this direction. So now I'm going to come back over here and write it. I'll put 0.56 on the left, and we're going to take the square root of everything now. Okay, I'll come over here with that. So we get this off the calculator. this right here. And then all of this just comes out. The square root undoes that square, undoes that square. Okay, multiply both sides by x. Add 2x to both sides. This goes away. That becomes 2.75x. This does. And solve for x. And we get this. Okay, we'll leave it at that. So that's our x value. Okay, and we can actually go one more digit here. So x is actually a concentration that we want to know. There it is, of H2 and I2. It's 0.182. And yeah, that checks out with what we have up there. Okay, so this one is simply going to plug this into that. So I'll come up here. I have a little more space up here. So I'm simply plugging 0.182 into this equation right here. Okay, so we're going to go ahead and do this calculation. 0.5 minus 2 times 0.182, and that gives us 0.136 molar for the concentration. Let me go right there of that. This is an incorrect answer. That was the answer that my source put, but it's not right. It just simply is not correct. Okay, so this is the correct answer for that. And for these two, XX, it's this down here, 0.182. So those are the concentrations of H2 and I2 at equilibrium. When the reaction reaches its happy spot and stops, that's what you're going to have. This much of HI and this much concentration of H2 and that same concentration of I2. All right, let's keep going here. We're going to knock down these Chatelier Principle problems. They're very logical if you think about them. It simply says if you do certain things to the reaction, like increasing temperature, pressure, concentrations, which way will the reaction move? So, you know, the term you want to use is it going to favor reactants, meaning moving to this side, or is it going to favor products, meaning moving to this side? So there's different situations that we're going to set up here. So here's a generic reaction of 2A plus B produces C plus 3D. And we're going to just assume that this is an exothermic reaction, meaning that heat comes out of it. That means delta H, if you remember back to thermochemistry, equals a negative number, in this case negative 32.4 kilojoules. Now in terms of the reaction, the way you include heat in the reaction, it's a product of the reaction. If heat is going to come out of the reaction, so we just assume that a reaction moves from left to right, and if it's exothermic, that means on the product side you're going to get heat coming out of the reaction. So you treat that as a product, in this case, for an exothermic reaction. So 2A plus B is going to give you 1 mole of C, 3 moles of D, and some heat. And it happens to be this much heat right here. But you add the heat on the product side because that's a product of the reaction. Okay? The fact that it's negative here simply means that it's like your bank account. When you take something out, money out, that's a negative to your bank account. When you take heat out, that's a negative to the reaction. But heat is coming out right here. You never have negative signs in a chemical reaction, or minus signs here. So heat is coming out there. Okay, so concentration of A is increased. This is kind of logical. Everybody's happy right now. You're in equilibrium. Suddenly you put more of this in than the reaction wants at that equilibrium. So what's going to happen? It's going to start pushing things to the right. You have more of this than you want, so everybody's going to start moving over to the right. So that's going to favor products. How about concentration of C? You increase this. Okay, so everything's at equilibrium. All of a sudden you start cramming more of this into the vessel, the reaction vessel, than this reaction wants. It's going to start moving backwards. It's going to start moving to the left. That means it's going to favor reactants. Okay, so again, pause and try to do these on your own, okay? Maybe you need to see a few of them first to get the idea. But once you've done that, then you only improve if you make your brain try to figure these things out itself. Okay, so pause and do that. They don't take very long, and then come back and see how you did. Just kind of test yourself. You should always be testing yourself. Do you know something? Do you really know something? Okay, concentration of D is decreased. So everybody's happy, and then all of a sudden you start pulling this out of the reaction. So what the reaction is going to want to do is make more of this. Wants to get it back into equilibrium by making more of this. So that's going to move to the right. Favor products. And I'll go ahead, if that helps, and just put right, means it's going to move to the right. Or maybe it's good enough to just draw an arrow like that. This is favor reactants, that's going to move to the left. Favor products, that's going to move to the right, okay? Now the temperature is increased in this reaction. All right, so let's think about what's happening. This reaction is doing what it does, and it gives off heat. It wants to get rid of heat in order to make it go forward from left to right. It wants to give away heat. If all of a sudden you plug that up and don't let it give away heat, you're going to slow the reaction down, possibly even stop it. So what is increasing the temperature due to the heat of the reaction? It forces heat into the reaction. This reaction doesn't want heat to go into it. It wants heat to come out. So if you increase the temperature, you kind of make it harder for the heat to come out into a hot temperature environment. So that's going to slow the reaction down, or in fact push it back to the left. So that's going to favor react going to the left. You say that one more time. This reaction naturally wants heat to go out of, you call this the system, it wants it to go out into the surroundings. If you turn up the temperature of your surroundings really high, then this heat gets jammed up in here. It can't get out because it can't get out into a hotter environment. Remember what heat does, it wants to flow from a higher temperature to a lower temperature. If all of a sudden your surroundings are at a higher temperature than your reaction is, then the heat can't escape, it can't get out. So you're basically plugging up the reaction and not allowing it to go forward from left to right. So increasing the temperature is going to push the reaction backwards. If it's an exothermic reaction, that's the key. Okay, so it favors reactants if it's exothermic. So temperature is decreased. Now you turn the room really cold. This wants to give off heat. It's much easier to give off heat into a cold room. It's much easier for that heat to escape out because there's a bigger temperature difference in favor of the heat leaving this hot reaction into a cold room. So if you make the room colder, it's going to be easier for the heat to escape, so the reaction is going to move to the right. So that's going to favor products. Again, another way to think of it, this reaction, by getting rid of heat, it's trying to cool itself off. Okay, it produces a reaction in heat. It wants to get rid of that heat. It wants to get that heat out. It's trying to make itself cooler. If you turn up the temperature in the room, it can't make itself cooler. If you turn down the temperature, then it's easier for this reaction to make itself cooler by getting rid of heat, and so the heat's going to flow out, so that's going to make the reaction flow to the right. Okay, let's keep going. Let's use a different reaction. This is an actual reaction now that we've seen before. Decomposition from NO2, a combination or synthesis from two NO2s into one N2. That should be N2O4. Doesn't really matter here. What's important here is the moles. And you'll see that in just a minute. And these are gases. This should also say gas. So they're gases. That's significant too. Okay. All right, so you increase the concentration on this side. Again, these should be N2O4s. It doesn't matter, okay? You increase the concentration on this side. That's going to throw it out of balance and make it want to go backwards. It's going to want to decompose this and turn into more moles of NO2. So that's going to favor reactants. Okay, concentration of this is decreased. Okay, so it's happy. Now all of a sudden you take this out, so it has less of this than it wants at equilibrium because you've just removed it. You've decreased this, so it's going to flow to the right. It's going to want to make more of this to get back in equilibrium. So that's going to favor products. concentration of NO2 is increased. This is increased. Okay, so it's in its happy place. All of a sudden, you pile more of this in than it wants at equilibrium. So it's going to start kind of decreasing this by starting to produce more of the product. So that's going to favor products. Concentration of NO2 is decreased. Okay, so equilibrium, all of a sudden you pull this out. It doesn't have as much of this as it wants at equilibrium. So this is going to start moving backwards and producing more NO2. So that's going to favor reactants. Temperature is increased. Okay, so this is also an exothermic reaction. That means heat wants to come out. So you can put plus heat. That's going to be a product of the reaction. Don't get confused that this is plus and this is minus. Minus means heat is coming out, like money going out of your bank account. But what this is saying is that if you include this heat in the reaction, actually write it as part of the reaction, this reaction is producing heat. That's why heat is leaving. It's producing heat. So you can think of that as a product of the reaction. N2O4 is a product of the reaction, and heat is a product of the reaction. So temperatures increase, so we talked about that before. You're making it harder for heat to escape if you increase the temperature of the surroundings. Okay, heat likes to come out into cold surroundings. It doesn't want to come out into hot surroundings. Why? Because heat is a transfer from higher temperature to lower temperature. So if this chemical reaction gets really hot and produces heat, and you make the surroundings really hot, it's hard. There's not much of a temperature difference between the reaction and the surroundings. The heat can't flow out. It's being shoved back in. So that's going to favor reactants. It's going to move back to the left. Since I didn't give you an example, this had been an endothermic reaction, so this had been a plus delta H. That means the reaction wants heat to go in. Heat going in makes the reaction go forward. Then as you increase the temperature, that would make the reaction go from left to right. Because if that would make heat over here, if it's endothermic, a reactant. And adding heat makes the reaction go from left to right. But that's not what this did. So it's not endothermic, so that doesn't apply here. Okay, temperatures decrease. That makes it easier for the heat to escape. If you make the room really cold, it'll be easier for this heat to get out of the reaction into the room. So that's going to favor products. Pressure is increased. Okay, this is where the moles comes in. So this is 1 mole of N2O4. This is 2 moles of NO2. So if we remember from the equation, PV equals nRT. This is number of moles, and this is pressure. So they're directly related. If you double the number of moles on the right side of the equal sign, you're going to double the pressure on the left side of the equal sign. If you cut the number of moles in half on the right side, you're going to cut the pressure in half in order to keep these two sides equal. So if pressure is increased, that means one way that you can decrease the pressure, because that's what the reaction's going to want to do. If suddenly you increase the pressure when it's at equilibrium, it's going to want to get back to equilibrium pressure. So how can it do that? It can do that. It means it wants pressure to go down. Okay, you made the pressure go up. The reaction reacts by saying, I want the pressure to go back down so I can be back in equilibrium again. That means what it's going to want to do is reduce the number of moles inside the container, okay? The number of molecules. Fewer molecules means fewer molecules are hitting the sides of the container. That's what we said pressure was. And so the pressure is going to go down. So what you would want to do is, what the reaction is going to want to do is decrease the number of moles. Again, you increase the pressure from the outside. The reaction is saying, I don't want that higher pressure. I want to get back to my equilibrium pressure, so I want to reduce it down. It's going to do that by reducing the number of moles. So how does it do that in this reaction? It converts from the side that has 2 moles to more of the side that only has 1 mole. In other words, if you started with all of this, you'd have 2 moles in your container. If all of that converted over to this, you'd then only have 1 mole in your container. That means your pressure would be lower. So by moving from left to right, the pressure goes down because you have fewer moles. So that means it's going to favor the side with the fewest moles. It's not always products, but in this reaction it is. The side with the fewest moles is products, So the reaction is going to want to go to the side that has fewer moles, fewer molecules in the container, so that it can reduce the pressure back down to equilibrium. So that means in this case, in this reaction, it's going to favor products. And I'll just write 2, arrow, 1. It wants to move in the direction of the 1. So it wants to go to the right. Okay, pressure's decreased. The opposite situation. You've decreased the pressure. Now it wants to get back up to equilibrium pressure. So let's be sure we know which problem we're talking about. This one is this. This one is this. So the pressure, it wants to increase the pressure. And the way the reaction can do that without you doing anything else is it can increase the number of moles. So if it increases the number of moles, it will increase the pressure back up to what it was at equilibrium. Remember, you did this. I'll write that here. You did this somehow by changing something in the reaction container, and the reaction reacts by doing these things. So if you decrease the pressure, the reaction is going to want to increase the pressure. It does that by increasing the number of moles. That means it wants to go from 1 mole to 2 moles. So it wants to go backwards. So that's simply going to be favor reactants. And that means it wants to go from 1 backwards to 2. It wants to do that. So it has more moles and therefore increases its pressure. Okay, that's how you do Le Chatelier. And they're pretty logical when you just think about them for a little bit. And I'll give you some more practice on those, I think, later on. Okay, last question. Explain briefly how catalyst affects the rate of a reaction and the equilibrium of the reaction. So very simply, you can say it in one sentence. Okay, so a catalyst increases the rate or speed of a reaction, but it does not affect the equilibrium. So the reaction is going to still get to the same equilibrium point that it would have gotten to, it just gets there faster. Okay, so that's the key to a catalyst. Okay, fairly long assignment, but very important one to understand how equilibriums work. And so if you've done these problems conscientiously, reviewed them, you should be good at this by now. We've covered kind of pretty much all of them. We're going to use this in acid-base reactions and in other reactions that we'll do for the rest of the course. So get this done. If you can't quite get it done by Friday, you should definitely try, but get it done over the weekend. However, you are going to get another assignment, a big one on Friday, so try to get this done as soon as possible. And we'll see you in class on Friday.